Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Gilles Chabrier and Romain Lenoble with us today. Hi, Giles. Hi, Romain.
Well,
How are you guys today?
fine.
Good. It is May 2nd of 2023 as we record this. And where are you two located at? What's your geolocation these days?
Well, right now I'm located in Lyon, but I'm spending part of my time in Exeter, UK.
Oh, yeah.
I'm split between two.
Very
two
nice.
parts of that.
Is it spring yet in either Lyon or Exeter, or we still sort of in the winter or summer?
Well, I think summer is starting in Lyon. It's getting warm.
Oh, okay. I am in Phoenix, and we are definitely moving into our summer months. We got our first triple-digit Fahrenheit the other day, so quite warm. Very cool. All right, and we'll start off with Romain. What do you like to do for research?
I'm now a PhD student here in Lyon on primordial star formation with Benoît Commerson and Joachim Rosdahl.
Very cool. And what is your when do you anticipate graduating?
Next in one year and a half.
Year and a half. Awesome. Well, I look forward to saying Dr. Lenoble. That'll be very nice. And Gilles, what do you like to do for research?
Various things, working on star formation and plasma physics and planets. Any interesting topic, cosmology, some part of it.
Ooh. All right. That's wide. Very cool. Very cool. And that is going to bring us to this very awesome APJ letter. So 2 points, people. First of all, it's open access. So you can go get a copy for free. Go grab one. And the other thing I want you to notice is this is a 17-page letter. Okay, so the primary metric for APJ letters is impact. Length is a secondary concern. Okay. Probing the Milky Way stellar and brown dwarf initial mass function with modern microlensing observations. And Gilles and Romain, take us away.
Okay, so maybe I'll just start with the general topic or explanation or purpose of the paper, and then Romain will go more deeply into the details.
Okay.
So the first question is, what is this a stellar initial mass function? I mean, I guess you guys know what a star and a brown dwarf are.
Oh yeah.
Okay.
Oh yeah.
Okay. So what's called the initial mass function is the number of stars in any galaxy in the universe per mass interval. It's dn over dm, or dn over d log m if you take a log scale.
Fair enough.
And it's crucial to find out what the so its nickname is IMF for initial mass function. So it's what nature has made as a number of stars per mass interval. And as you certainly know, I mean, the IMF determines basically all the chemical, energetic, and bionic properties of the universe. Because, roughly speaking, to make a long story short, let's say that most of the stars more massive than 8 times the solar mass finish up being supernovae. And so you have a lot of nuclear ejector, and from these nuclear ejector, you have the chemical evolution of the universe. We are part of, because as a matter of fact, we are built with the rest of the primordial supernovae. Then, roughly speaking, stars between, let's say, 1 and 8 solar masses make most of the mass of the universe.
Yes.
Right. What's called the baryons. And stars below that, which are the brown dwarfs, are very difficult to detect because they are not luminous. And I mean, they're not very luminous.
Yeah.
So it's difficult to find to observe them with regular telescopes. So finding out what are these fractions, which are determined by the total stellar initial mass function, from the lowest type of mass of star, which is the lowest brown dwarf masses, which are a few Jupiter masses. So to give you an idea, Jupiter mass is 10 to the minus 3 times the sun mass. So you want to find out what is the initial mass function between, let's say, 1 Jupiter mass and more than 100 solar masses to cover the entire stellar mass range.
Waiting.
As I said, so the standard way to determine this stellar initial mass function is to look for the light of stars and brown dwarfs. And from the light, the observers come up with light magnitude, right?
Yes.
And then you have theoretical models which enable you to transform the light into a mass. For a given light at a given age, you find out what the mass will be, and then you get it. You have the dn over dn.
Yes.
From brown dwarf, it's much more complicated because, first of all, as I said, these guys are very faint, so it's very, very difficult to find them out. Number two, in the brown dwarf regime, the stellar initial mass is decreasing, so you don't have a lot of these guys around.
Yeah.
And last but not least, whereas stars reach what's called a nuclear equilibrium, meaning that for the sun, for instance, after something like 5 or 10 gigayears, the star doesn't evolve anymore. So no matter what the age will be, after, let's say, 1 billion year, between 1 billion and 10 million, the sun will be the same. So you don't care about what the age will be. For brown dwarfs, it's a different story because by definition, these guys do not reach a nuclear equilibrium because they're not massive enough to sustain hydrogen ignition, hydrogen fusion.
Yes.
So they are not only their mass depends on their light, like a star, but it depends on their age. So it's a much more complicated topic to find out. You need to know the light, to observe the light, and you need to know the age. So the easiest way to do that is to look in young clusters in the galaxy because you have, roughly speaking, the edge of the cluster.
Yes.
So at least you have the edge, and the light is going to give you the mass, but the statistic is going to be small. The other way is to use a kind of a probabilistic approach, which is what the microlensing experiments are meant for.
Cool.
Meaning that in that case, what is a mass? So that number 2 of the title, what are the microlensing experiments? We know from general relativity and from Einstein's equation that when you have a light emission very, very far away from you guys, from us, okay, and as these light rays travel across the cosmos and reach us, if there is a dark body, let's say, if there is a body with a gravitational potential in the path between the light emitter and us, because of the general relativity effect, these light rays are going to be enhanced, so to speak.
Yes.
So it's exactly like the glasses you're wearing today. It's going to increase the number of photons, right? Say, okay, so you have more photons because of this lensing effect than you would have if nothing had happened.
Yes. Cool.
So these brown dwarfs you do not necessarily see by light. They do have a gravitational potential, meaning that if you pick up a source very far away from us, for instance, in the center of the galaxy, by the way the light travels from the center of the galaxy toward us, towards the sun, they're going to be these light rays are going to be influenced by all the gravitational potential they're going to cross, including the brown dwarfs.
Yes.
So, and then you're going to have an amplification, as I said, because of this lensing effect. You're going to have an amplification of the light source, right? Okay. Now, So and of course you have a lot of statistics, because if you're looking at the center of the galaxy, I mean, you're gonna have billions and billions of brown dwarfs. Point is, you're gonna have three unknowns in the story. First, you don't know the mass. Two, you don't know the distance, and three, you don't know the velocity, because you know this brown dwarf is not going to stay forever between the
on the cosmic
and us. It's gonna keep moving, because it does have a motion. So these three unknowns are unknowns. You must determine, statistically speaking. It's exactly the basics, the heart of the so-called microlensing experiments or microlensing equations. So it's essentially what Romain and I have been doing, is to try to use the most recent microlensing experiments by the Polish group, which is called Ecole, for optical gravitational lensing experiments. Right? These guys are experts. Have been experts in the field for the past 30 years, and now they have billions of objects they've observed, and Romain and I mean, derive the tools to analyze their statistics as accurately as possible.
Cool.
Now, and with the ultimate goal of nailing down the initial mass function, or at least excluding, I mean, making a choice, or let me rephrase it, comparing different initial mass function models, which have been suggested in the literature.
Yes. Cool. Very good.
This is the basic of the story.
Awesome. Very cool. Okay. Then we move into, want to talk about the bulge? Want to go into the mass function? What would you like to do?
Maybe Romain can explain what the bulge is and what the disk. Maybe maybe Romain and I can explain basically what are the basic building blocks of a galaxy: bulge, disk, and halo. Romain?
So the idea is that we have Gilles told, that the system is completely degenerated, because when we measure, the only stuff we measure is the time, the duration of a lensing event.
Yes.
Which are around 40 days. But this time depends on the velocity, the mass, the position, and the impact parameter of the lens compared to the source.
Yes.
That means we just measure one parameter, and you need to derive a lot of parameters from just one measure. That's the main trick of this principle.
Cool.
And for this, you need to do, so the only thing to get is to do statistics. So thanks to Ecole, they have detected a few thousand events. And if you get a model that's saying, well, we are expecting a lot of stars close to the galactic bulge, then less in the disk, etc. And you can also derive velocity properties for these stars. Then you can compare the statistics observed as the statistic you derive.
Yes.
So what we did is that we created a galactic model that can reproduce the stars and the property of the stars in the galaxy. In the galaxy, So the Ecole experiments we use were inside the galaxy. So usually microlensing experiments aim at a really dense area, because it's a very rare phenomena. And if you aim at a place where there is a lot of stars in the background, for example, the galactic bulge, then you expect to have much more events, because you need a lot of background stars, source stars, to have a lot of event. So the main study we use in the article is to the galactic bulge, which is the densest area of stars that we have.
Cool.
So we need to do a galactic model towards the galactic bulge. So for this, we model stars in a few parts. First, the bulge, which is the galactic center. So we can use a model. I don't remember the name of the model, but we use a model, the double exponential for to Bakkelson. We also use we assume velocity dispersion and rotation for the stars of the bulge. So for this, we use Gaia data with an asymmetric dispersion. And then we model the galaxy, for example, the disk. So we use a thick disk and thin disk model with different velocity and different density.
Yep. Cool.
So that's the main. So we have to measure the mass, and for this we use a uniform mass function. So and we compare. Once we have our fiducial model, we compare with different initial mass function. So that's the point. That's the whole framework of this work, is to have a fiducial model and then compare with different mass function. So we have just briefly we have tested, because you can imagine that there are many models for the bulge, for cinematic, etc. So we have compared in the appendix B how much it differs if we change only for example, the galactic bulge, the mass of the bulge, etc. in appendix B. So here are all the fiducial, so our fiducial model and all the different tests.
Maybe we can explain roughly what is a disk, a bulge, and I mean, a galaxy, what's called a galaxy, or let's say a Milky Way-like galaxy, spiral galaxy, has, roughly speaking, 3 parts. It has a very, very, very large halo, stellar halo, dark halo. And the pioneering Microlensing experiments in the late 90s, the mature Eros ones, were trying to probe the halo, and it brought some interesting results. But the ones we are interested right now are not devoted to the halo; they are devoted to the center of the galaxy. And the center, the 2 other parts are the very center of the galaxy is what's called the bulge. You know, it's like a puffy, like a little bit like a American football ball, you know, like a rugby team, if you wish. You know, it's like a puffy, and it's very concentrated near the very center of the galaxy, but from as a result of its formation process, by the way. And then further away you go, you know, because galaxies are rotating, you have the centrifugal force. You get something flatter and flatter, right? Which is a disk, and the sun is located in the disk of the galaxy. The sun is located at something like 8 kiloparsec away from the center of the galaxy. So from an experiment, from a Microlensing experiment, which is based on the sun, let's say on the Earth, because you do have to take into account the motion of the Earth around the sun. You look toward the center of the galaxy, and then you're going to have Microlensing events in the disk and Microlensing event in the bulge, and you'll have a lot of degeneracy. You may have a galactic event, brown dwarf, or call it the way, in the bulge due to a source in the bulge. So it's a bulge event. You might have the same thing in the disk. So it's this disk event, and you may have a cross event like a source in the bulge and an event in the disk, which is a galactic, a bulge disk event. So you have to test all these hypotheses. So you have to test a lot of reliable galactic models, which come from other constraints, and Romain mentioned Gaia or other ones, and basically the list you have in table 1 of appendix B. And the punchline, because you don't want your result, the holy grail is to determine the IMF. So if the results depend too much on the galactic model you're assuming, you're dead. And as a matter of fact, so it's for instance, if you pick geometry, this is the angle, this bulge, which is more like a bar, as an angle compared with a disk. This is, for instance, what the phi parameter is meant for. Or you have other stuff, you have the velocity dispersion, whatever. But the punchline in that, so we spend months with Romain checking out various models, And the
Cool.
punchline is that the IMF, the results depend more on the IMF than they depend upon the galactic bundle. So punchline is that we're on a safe track.
Yeah.
We can all the difference. We can say that the differences in the Microlensing distribution will stem primarily from the IMF.
Good. Excellent. Very good. Okay, I'm with you. Okay, let's slide back up to where we were before we got down to there. So we went through the bulge, we went through the components, we went through our disks. Here's our
Just
disk.
for instance, if you go to figure 1, I believe, if I recall
Go
correctly.
to figure. Figure 1. Here we go. Comparison of some histograms.
Romain can okay. So Romain can comment more on
So
that.
now we can focus on the results.
Yes.
So figure 1 is showing in the galactic plane the value of tau and gamma and TE. So tau is what we call the optic depth. Optical depth corresponds to the number of events we observe
And the mass.
and the mass.
Yes.
So we can see that. So we added MOA, which is a Japanese experiment, because they have computed the optical depth, contrary to, but it didn't have computed the gamma and Milky. That's why they are not on the right.
Okay.
But the main experiment is Ecole 4. As you can see, the errors are much lower.
Yeah.
But we can see that here we vary with the parameter beta, which is influence in the density of source star.
Okay.
So we can see in the appendix. Maybe it's not relevant.
Let's go there real quick. Let's take a look at data.
It's not really relevant, but maybe I think it's appendix C, maybe, or after.
I'm not sure we really want to dig too much
Yes.
into the appendix because you're gonna lose all the audience.
Yeah. We'll remember
Anyway.
what data is. We'll
It
remember
depends
what
on
data
the
is.
number of source star.
Okay.
And so the main point is that in the galactic plane, our model fairly reproduces the data from Ecole 4.
There we go.
Both in tau, which is optical depth, gamma, which is a number of.
Pretty good. It's pretty good.
Right.
Pretty good.
Then it's a mean time, mean TE.
Yeah. Mm-hmm.
You can see that
Yes. It's very
a
good.
long event, like between 25 and 30 days. So you can imagine that it's really tough to observe because you need to observe for a few each night, many times per night, even the same area of the sky.
Mhm. It's an awesome observational campaign to get this. Yep.
Yeah.
Very good.
Well, so what's important is figure 1 is, as Romain said, it's basically the tau, the optical depth, depends on the distribution of mass between you and the source.
Right.
Okay. So it's an integrated quantity. The rate is the number of events per day, per whatever. Okay. The total number per day. And the average Einstein time is a crossing time during which you have this amplification. But so these results are let's say the bulk results of the calculations.
Cool.
So
Okay.
it's the integrated values. So so it's a number 1 on your item on your checking list, because if you fail having the gross results, then you're in you can go back and start from
Start again. Very
so
good.
at least so this is the first thing you want to check.
Good.
And as Romain said, you say, let's say that so far we're on the right track.
Right.
Okay. So
very good.
But it's not, since it's integrated values, you don't have what you look for, which is a differential value, which is the n over the m. You don't have the result as a function of the mass, which is in microlensing. Remember, you're sensitive to the crossing time, so you have to convert this crossing time into a mass, and which much more detailed, and which is the topic of the figures 2, because the one just below. So now we are reaching the heart of the problem, because you you have a time distribution between 1 day and 300 days, which, roughly speaking, means you can have kind of a bijection. It's not a bijection because, as Romain said, it depends on the whatever. But roughly speaking, the smaller the time scale, the smaller the mass. The larger the time scale, the larger the mass. So it's almost like if you had this time distribution is almost what you would have as a mass distribution.
Okay.
And the mass distribution is what you're looking for. And all these curves right now are the results on the time distribution for various IMF models. And as you can see, and the statistic is pretty good because you see the error bars. As a matter of fact, you see that there is only one IMF model which basically goes across all the error bars. So the left-hand figure in the, I don't remember exactly what.
Black and yellow.
Yeah, so I think so C05 stands for Chabrier 2005. It's my model of 2005.
Yes.
And you see that it's basically the only one. So the difference between blue and red is a correction, is an experimental correction. We don't want to go into the details.
Yeah,
you have to focus on the red curves. And you see that on both figures, you have there's only one the IMF which reaches the best agreement with the observed time distribution is a CO5 one.
Good. Okay.
Compare with the Krupa one or the CO3 one.
Yeah, those are popular ones.
And the dashed line is the distribution which comes only from brown dwarfs.
Okay, got it. Good.
So already at this stage, you can say that there is the most favorable IMF is a CO5 IMF, and the other ones are excluded because they cannot reproduce all the time distribution.
Yeah. Very good. Cool.
Okay. It's the only microlensing events, as I said in the introduction, are the only possibility to nail down these IMF down to a few Jupiter masses, which means down to basically a 1 day amplification duration.
Nice. Very nice. Very cool. Very cool.
And just so now, if you want now to go to Appendix B or C, if I recall.
Let's go to Appendix B. It was the characteristics of mass function, and C was.
Okay, let's stop here. Okay, this very complicated figure you see is a mass distribution. It's what you're looking for. It is the in log scale, log of n over d log m as a function of d log m. And going from right to left, you go from very massive stars down to Jupiter mass stars. And all these various lines or curves stand for the various IMFs which have been suggested in literature, which are parameterized in the table just before that.
Yes.
And you see that whereas most of these IMF are consistent in the mass scale from 1 solar mass, meaning log m equals 0, upward, which is what's called the saltpeter historical IMF. But now, when you reach lower masses, let's say below 0.1 solar mass down to Jupiter masses, you see that you have huge differences.
Yeah.
IMF predict a lot of brown dwarf compared with stars, other ones not as many brown dwarfs as the other IMFs. And it's exactly so when you carry out all the calculations, it's exactly what you get when you look at the mass distribution we were talking about previously.
Yes, I'm with you.
So as I said, there is not a one-to-one, but there is a correspondence between these IMF and the time distribution we were looking at.
Yes. Very good. Very cool. Okay. Whoops. Online.
I think it's fair to say that there is only one IMF.
That's right. There's only one, presumably.
Presumably, we always have to be cautious in science, as you know. But presumably, it's these IMF. We already know that this IMF, this CO5 IMF, is consistent with all the light observations in young clusters or in the galaxy like this.
Okay.
Within a factor of 2, maybe, not even within 10 to 20, 30% if you wish.
That's pretty good.
But let's say it's a fairly reasonable description of the mass distribution in the Milky Way, and then in other galaxies.
Very nice. Very nice. Okay, so that was appendix B and C. Let's see. Want to cover figure 3? Figure 4?
So figure 3 is the same as the previous figure. Number of events per time.
Yeah.
And here we focus on only the most central field of Ecole 4 experiment. So we aim to the bulge and only the center of the bulge.
Right.
And this field were observed with a much higher frequency, meaning that we can detect much shorter event with a better efficiency.
Okay.
That's why they have events that are less than one day. You can see on the left with they detect a few events like this. Which we do not model because they were probably extremely low mass events.
Okay.
So the main aspect is that the shape of the histogram is really different than the shape of the global histogram of the bulge. And this is despite the difference in efficiency.
If you compare the observed histogram, this figure, with the one in figure 2, you see that independently of on any theoretical model, the histograms are different. I mean, the scale is not the same, but if you had time to look at it more closely, you'd see that you have many more short time events in the figure 3 than in the figure 2.
Yes.
Meaning that if you look at the very centermost fields of our galaxy, you do have much more low mass stars and brown dwarfs than in the solar neighborhood, which is a puzzling question. And which something which has been observed indirectly, looking at what's called in high redshift, when the universe was less than 1 billion years old, you had a formation of what's called massive early type galaxies.
Okay.
And we have a lot of observations now by what's called integrated spectroscopy. Observers are able to determine what's called the mass to light ratio.
Yes.
And these all these observations point to a mass to light ratio of these massive early type galaxies, which is much larger, let's say between a factor of 2 and 3, than the mass to light ratio in standard spiral galaxies.
Okay.
Meaning that in these very early galaxies, the nature was able to make much more low mass objects, meaning more low mass stars and brown dwarf than today. So so the puzzling question is so meaning that what is the star formation process, which is something we are working on and many people are working on worldwide, and is there an explanation for the reason why these massive early type galaxies made more stars? And interestingly enough, we get exactly the same result looking at the bulge of our own galaxy. And the bulge of our own galaxy, it was by definition formed very, very early in the formation of our galaxy. So there is a hint that the formation process in the bulge of the galaxy was very similar to the one at high redshift in galaxies.
And that's very convenient. That's very nice.
So it brings a lot. So it's an indirect information upon the fact that that the early stages of galaxy formation were different at that time than now. And now the reason is why. And according to some theories, we worked out with some colleagues of mine, and Romain is working on that now. We suggest that the turbulence and density
Yeah.
are very are the key factors in star formation.
Yes.
And we know that in the early universe, the universe was denser and more turbulent than now. So was the bulge.
Cool.
So we suggest that, there is a common explanation.
Very good. That's very nice.
We may be wrong, may be right.
Sure, of course.
But for sure,
we will come to that. We will come to that.
But for sure, you can say that the IMF is different, as Romain said. You can say that the black curve, which was fitting perfectly the global galactic model,
right.
Now it's completely out.
Right.
So we now we reproduce this result with what's called CHC14, which stands for Chabrier and Bell Charlot 2014.
Okay.
Which was the IMF we had suggested for massive early type galaxies.
Okay. Nice. Very cool. Which
does a better job when you look at the centermost fields of the bulge.
Yep. Very cool. I think we got one more in the main body, if we want to say where it is, CHC14. There we go. And I think we have one more figure we may want to cover, and that is the average optical depths rates.
So this is now actually in the Ecole 4 experiment, they also aim at the disk, so in every direction, not in the bulge, so in the other direction in the galactic plane.
I'm with you.
So the problem is that you have much less source star in this area, because as you can imagine, there is no background stars. So this was more like a test for our model, but it's not the main result of the article. So as you can see, here we have the galactic longitude, and you can see that, for example, the tau, so the optical depth, fits quite well.
Yeah.
The galactic longitude.
The number you got, yeah.
Same for the number of events, gamma. But then for the second point, as a function of latitude, we see that our fit is not bad, but it still do not match perfectly the observer. There is some points that are a bit above or below, and thus we have not a clear explanation. It's maybe linked to the fact that there are over densities in the disk, in the background of stars, because our model is only exponential and has no dependence on the direction. So that might be linked to
Got it.
and that's that was like more a test to compare with whether our model fit in the not necessarily in the bulge, in the other direction, and it was quite good at first, so that's why we added this. But that's like secondary result of the paper.
Cool. Very good. Very good. All right. And that will do. And I do want to just remark to people, there are some pretty awesome appendices in this letter. We got 26 equations in there. You can go through the detail on the IMF and the microlensing calculations. I do encourage you to check that out if you're interested in the global details. Very good. Gilles and Romain, I want to thank you so much for walking us through your very lovely APJ letter. Thank you.
You're very welcome.
And you mentioned it twice a little bit, or you hinted at it a couple of times, and I want to push on that and follow up a little bit. So where do you think we go with this, let's say over the next 2 to 5 years? Is ALGO going to be putting out more data? Is there other telescopes that may be able to help, JWST, Roman, etc.? Is there additional theoretical work that can be done? Is there going to be a Chabrier 2023 IMF? So just sort of where do we go with this topic in determining the IMF at the low end of the mass scale over the next couple of years?
I can see two interesting ways to nail down even more precisely the IMF. The first one is one connected with microlensing experiments, and you mentioned it. It's a Roman space telescope, formerly the W1st space telescope. So this I'm not sure when Roman will be launched. I believe it's in the near future or something.
It's in the near future. It's in the mid-20s. Yeah.
Yeah. And so they're going to be looking at microlensing experiments. So we're going to have more statistics than Argyle. And interestingly enough, they're going to be doing microlensing observations in the infrared. So you know that these low mass objects, as I said, are faint. If they're faint, they're cool. If they're cool, their light is emitted more in the infrared than in the optical. So we have a lot of data, statistics, and improving the data. So that will help for sure from the microlensing point of view. And from the observational point of view, there is a WISE survey, which is already working. And WISE observes the light of very low mass objects down to a few Jupiter masses in the galactic disk. And it's basically the PI is Chess Beckman at Caltech or at IPAC, which is IPAC. And so we already have interesting constraints from WISE, and hopefully we'll have more constraints in the years to come. So we will definitely have more constraints in the year to come.
Cool. Well, I really look forward to seeing us nail down the low end of the IMF here over the next couple of years with some of these new facilities and new work, just like the steps you're doing. It'll be really great. So thank you. Gilles, Romain, thank you so much again for walking us through your very lovely article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.